I'd like to welcome you to Atmospheric Sciences 5000, an introduction to atmospheric sciences. This course is super exciting because we're going to put equations on everything for the very first time. My name is Kevin Perry, and I'm a professor of atmospheric sciences here at the University of Utah. I've been in the department for 25 years. I'm a past department chair, and I started off growing up in Kansas and went to Iowa State University for my bachelor's in meteorology, went to the University of Washington for my graduate degree, did a postdoc with the National Park Service at the University of California, Davis, and I'm really an expert in air pollution. People in the state tend to call me Dr. Dust because for the last 10 years I've been spending my time researching dust coming from the Great Salt Lake and other playas in the Intermountain West. I love looking at the Earth from space because you see all sorts of different spheres of influence. You see the atmosphere, you see the lithosphere, you see the hydrosphere, the cryosphere, the biosphere. You can see it all from space. But more importantly, when you look at the limb of the planet, you can see this very thin veneer that represents the atmosphere, and everything that we hold dear is within that atmosphere. The topics that we cover in this class are intended to be a survey of the broad areas of atmospheric sciences. We start off covering thermodynamics, then move on to cloud physics, radiative transfer, and atmospheric dynamics. For the atmospheric science majors, you will take classes in each one of these disciplines that go into much more detail than what we're doing here in this class. In this class, we don't have calculus as a prerequisite, so I'm not able to derive the equations that we'll be using, but we will be presenting the equations for these topics and then learning how to use them. So what is atmospheric thermodynamics? Well, it's really just the branch of physics that's dealing with the transfer of energy between heat and sensible and latent heat. And it really talks about how we convert energy from one form to another, but it always relies on the fact that energy can neither be created nor destroyed, it can just change form. So when we put heat energy into a system, how will that system respond? It's all controlled by thermodynamics. Cloud physics is basically trying to understand everything that leads to precipitation from clouds. So we'll learn about the importance of particles in the atmosphere, the water vapor in the atmosphere, the process of condensation, the process of coalescence, ice crystal processes. All of those go into understanding how thunderstorms form, how general precipitation forms. Radiative transfer is looking at how radiation is propagated through medium, how it is absorbed, scattered, reflected, transmitted, all of those sorts of things, and we'll put equations on all of those so that we can quantitatively describe what happens to a beam of radiation as it starts to move through the atmosphere. And lastly, we'll deal with fluid dynamics, which is describing why the atmosphere moves in the way that it does. We'll do this by identifying all the different forces that act on an air parcel, and both the horizontal and the vertical. And putting it all together, we'll come up with some rudimentary equations called the Navier-Stokes equations, which actually describe about 90% of what's going on in the Earth's atmosphere with regards to motion. So the prerequisites for this course are just college algebra and general chemistry. As I said previously, without having calculus as a prerequisite, I can't derive the equations that we'll be using, so that we'll spend a lot of time trying to understand the assumptions that go into the equations and learn how to use those equations to answer questions about the atmosphere. The textbook is a free textbook called Practical Meteorology, an algebra-based survey of atmospheric sciences. It was written by Roland Stoll, who's a professor of meteorology up in Canada at the University of British Columbia. And I think at the end of the class, hopefully we can all send Roland Stoll a thank you note for his service. He got really frustrated with the high costs of textbooks for students and decided to write his own textbook and make it freely available for everyone. And I think that's a great service to the entire community and especially the students. Class workload. This class is going to be challenging, not only because the material is challenging, but we move at a fairly brisk clip. So in order to try and keep everybody on track, we're going to have weekly quizzes, and these quizzes are going to consist of about 5 multiple choice questions. You'll have 2 opportunities to complete the quizzes. You get to do it once, see what you got right, see what you got wrong. If you got something wrong, you get to take the quiz again to try and do that. Quizzes are for learning, so I expect everybody to get 100% on the quizzes all the time. We're also going to have 10 homework assignments, which will take the concepts and move them into more difficult assignments. We're going to have 3 in-class exams and a non-comprehensive final exam. This class used to be taught Monday, Wednesday, Friday, but we moved it to Monday, Wednesday, which gives us 80-minute class periods, which I think is sufficient for a reasonable in-class exam. Grading policies. The grades will be based upon the homework, the quizzes at 30% each, and 10% each for the 4 exams on thermodynamics, cloud physics, radiative transfer, and atmospheric dynamics. Final grades, basically if you want to get an A, you need 92.5% or greater, and you can see how everything falls out from there. So what resources are available in Canvas? Well, we have a detailed syllabus, which is intended to be my guide on what I'm supposed to be covering and what assignments you should be doing. We'll also have equation sheets there. The links to the e-textbook are there. We have pre-recorded lecture videos. This course is flipped. You need to watch the video lecture for the topic before you come to class, because I'm not going to be doing lecturing in class. Instead, we're going to be solving problems using the equations that were introduced in the video lectures. So that's extremely important. In order to be able to participate in the class and get the most out of the class, you have to come prepared. Other things that are available in Canvas include the grades and any announcements that need to be made as well. I'm really looking forward to this class. This is my favorite class to teach. I haven't taught it in 3 years, so I'm really looking forward to taking you all on a learning adventure about the atmospheric sciences.